Okay, so what is 2 plus -1 minus 2i?
One minus 2i?
Right, yeah, again, we have a 1 minus 2i. We're combining the 2 and the minus 1 for a positive 1. And we have our negative 2i. Okay, then we gotta multiply again. 1 plus 2i times 1 minus 2i. We'll do that here. 1 plus 2i times 1 minus 2i. What's 1 plus 2i times 1 minus 2i? -5. Look, the -5 came from 1 plus 2i times -1 plus 2i. That's not exactly what we're multiplying here. The first factor is the same, 1 plus 2i. But notice, when we compare 1 minus 2i to this factor here, they're opposites of each other, right? 1 minus 2i, this factor is -1 positive 2i. So we shouldn't get a -5, we should get a positive 5, right? Those two factors are opposites. This is the opposite of this. But remember, this thing that we're now multiplying fits that sort of shortcut when we said, here's a complex number multiplied by its conjugate. And we said when we multiply complex conjugates together, that result is just going to be the first thing squared plus the second thing squared. No i's involved. So we have this result is 1 squared plus 2 squared, which is 5. So we have that 5 going here. And then we have -5 plus positive 5, which is, whatever color that is. That gives us 0 here.
I think closing the lines might help.
Might?
Lighting.
Okay, we can try that.
So what you did there though, could you also just do it like normal multiplication and it should work out too?
With the last two factors we
Yeah.
multiplied? What do you mean by normal multiplication?
I mean like the normal like FOIL or whatever, how
Yeah.
you do it. Could you do it that way and you should come up
Of
with the
course.
same answer?
Yeah. Is it a little better? It's still pretty crummy.
It's a lot better.
All right. So what we have is a 0. What is 0 here?
The remainder.
That's the remainder. You've got a 0 remainder, which means is 1 plus 2i a 0 of that function? Yes. The remainder is 0. Thus, x equal to 1 plus 2i is a 0 of f of x. All right. Questions on that example? Yeah.
How would we rewrite that? We don't know this equations that was the consequence of the x squared.
Yeah.
How would we write that with the 1 plus 2y? We just like put in parentheses and start with x?
Yeah, right. Because remember these numbers here below the line,
Yeah.
these numbers here are the coefficients on our powers of x. So those are just the numbers. This is attached as a constant, so no x with that one. We've got a negative x for this one. This is our coefficient on x squared, and this is our coefficient on x cubed. And yeah, we just put those numbers in parentheses in front of the x squared. So like, we ran out of room. We don't see those things when we ultimately end up factoring these, but yeah, we would have an x cubed. We have -1 plus 2i. That's the coefficient on x squared, so it would look like that. Minus x plus our constant 1 minus 2i. But we don't deal with polynomials that have imaginary or complex coefficients.
Because we would be trying to find what the zero is, right?
Yeah.
And he wouldn't plug in x, or minus, sorry, 1 plus 2i, because we're the ones plugging them in the numbers.
Yeah, right. We opted not to go that route either. That was our first option here. We could use the remainder theorem, and we opted not to plug 1 plus 2i in for all these x's.
Normally, if we're given this problem, though, we're the ones coming up with what we plug in, right?
No, the what you plug in is given. So here, it's if this is a 0, then we should plug that in if we're testing whether or not that thing's a 0. So that would be like given to you in the problem.
If it was the other way, I would ask, what is a 0 of?
Yes, right. If nothing was given to you, it would say, hey, here's this function, x to the 4th minus 2x cubed, etc. And it would just kind of be hanging out by itself. And then it would ask you, what are the zeros of that?
You have to come up with 2.
And you have to factor that. Yeah, and ultimately something like this would have 4 factors or 4 zeros because it's an x to the 4th. But
So
remember,
if you took the x to the 4th off, but then it would be 3 and then 2. Is that how that works?
yeah, right. If we didn't have that x to the 4th there and our function were just 2x cubed,
Right.
it would have 3 zeros.
Oh, okay.
If we had a quadratic, quadratics always have 2 zeros. Yeah, so we get that theorem in the next section. And remember, like, it's really disjoint at this point because we're saying, all right, well, here's something that helps us divide. Here's something else that helps us determine whether or not we have a factor. Here's another technique that we can use to determine the very same information. And so we've got all these different pieces, and it's not until the next section these individual pieces really come together to form like a complete procedure. So we are looking at it in a very choppy manner right now. But remember, once we know we have a 0, we had this the following. If I know the zeros of a function, then consequently I know the factors. If I know the factors, I can also state what the zeros are. So it's like a two-way street here. We can move back and forth between zeros and factors in a specific way. We made mention of that on like the second page, but here it is again, and we'll see the theorem in the next section, but we might as well mention it right now. If x equals to some number k is a 0, or an x-intercept, or a solution, then x minus k is its corresponding factor. So essentially, when we see what we'll see in the next section, like right off the bat, is this thing right here. This is called the factor theorem. But this is pretty much the end of 3.2. Does anyone have any other questions about 3.2? Okay, so then in 3.3 we get a couple more pieces to put together to ultimately factor all of these now. So we're going to look at the factor theorem, the rational zeros theorem. The number of zeros, that's just what we spoke of. If you've got x to the 4th power, you'll have 4 zeros. If you have x to the 3rd power, you'll have 3 zeros, so forth. So conjugate zero theorem, we don't really utilize that a lot. It's just nice to know. And then we'll look at like finding zeros or factoring polynomials completely. So there's our factor theorem that we mentioned on the previous page, or the last page of our previous section. And it says that if x minus k is a factor, then x equals to k. Remember, this is our input. x equals to k is 0. And that's our definition of a 0 right there. So all that's really telling us is if we know the factors, we know the zeros. If you know the zeros, you know the factors. Okay, we're going to start off with this example. And we want to know, is x plus 1 a factor of the following function?
So if it's asking if it's a factor, it's just asking if you can come up with an answer, not a 0.
They're one and the same.
Okay.
Remember, so this question, we looked at an almost identical question in 3.2 just a minute ago. If the question is this thing a factor of this function that's given to you? Another way to state that is x equal to what value? -1. Is x equal to -1 a 0 of f of x? Those two questions are exactly the same question. Because remember, if we have a factor of a number, what's the result of us dividing that number by that factor? We get some sort of quotient, but always if something is a factor, what should the remainder be? 0. So another way to ask this is when f of x is divided by x plus 1, do we have a 0 remainder? So all three of those questions are exactly the same.
Can you either solve with it as -1 or do something division?
Right. So we can either plug -1 into the function to see if we get 0. We could do synthetic division with x plus 1. Those are our two options. If it's a factor, the remainder will be 0. Okay, so what do y'all want to do? Do you want to plug -1 in, or do you want to do synthetic division? Okay, plug -1 in. So we're gonna look at our question like this here and utilize the remainder theorem. Again, I wouldn't ask you like on the exam, what is the remainder theorem? It's just, it comes out in practice that you need to know what it is, right? That's when I take the function, evaluate it at my 0 or my potential 0 to see if in fact it is a 0. So we have -1 cubed plus 2 times -1 squared minus 5 times -1 minus 6 is what we're evaluating. So we just need to figure out what that value actually is. 0? Did you get 0? Okay, somebody got 0. Anybody else? Got a few confirmations. -1 cubed. -1 squared is 1 times 2. -5 times -1. And then we have our -6. So we have -1 plus 2, that's a +1, plus 5 is a +6, minus 6 is 0. So what's our answer to the question? Yes, x plus 1 is a factor of the function x cubed, etc., etc. And that's because we have a 0. Remember, that's our remainder. So yes, x plus 1 is a factor because we have a zero remainder. Does anyone have questions on that? Very, very similar to what we did in 3.2. It's just phrased differently, but you are talking about the same thing. Okay, what if we wanted to know now, what if we were to ask the question, what are the other factors? What are the other factors of f of x? In other words, when we say our f of x is the x cubed plus 2x squared minus 5x minus 6, we'll see in a little while, but our sort of what's guiding us is the fact that we have an x cubed, right? It's like the highest power we see on x. This thing should ultimately factor as three things times each other. So in other words, what are those factors? Well, we know one already, right? We know one of them is this one here, x plus 1. So x plus 1 is a factor. What are the other two? Or how do we find them? Synthetic division, right? If I told you 35 is a factor of 70, how do you find the other factor of 70? You have to take 70 and divide it by 35. So we have to take our f of x and divide it by what we know as a factor. So at this point, in order to find these other two factors here, we have to use synthetic division. With what we know is true. We know that x plus 1 is a factor. And again, this is what we're doing. We're just going to use synthetic division to shorten this process. Right? We've got to perform this division, which is equivalent to our coefficients on the inside, 1x cubed, 2x squared, minus 5x, and minus 6. We're dividing by what's out here in synthetic division. What's out there? Right, -1. So whatever we get below the line, except with the exception of the remainder, is the other factor. Okay, so we have plus above the line. Drop the first one down, so 1 comes straight down. Then we multiply by -1, so we get -1. Plus 2, positive 1, again now times -1 again, -1, plus -5, -6, times the -1, so positive 6, gives us a 0. And we already knew that, right? Our remainder theorem told us that that should have been 0. The same 0 we came up with in the first computation. But more importantly, synthetic division gives us this thing here. So what do those numbers correspond to? X squared plus x minus 6. Do y'all agree that that's x squared plus x minus 6? Here's our constant. Remainder constant x squared. That's always the pattern below the line in synthetic division. Remainder constant x to the second, so on. So this actually tells us that it's x squared plus x minus 6. Remember, what we divided by was x plus 1. We already knew that was a factor. So x plus 1 times x squared plus x minus 6 gives us our original function. Those are two factors of that x cubed function.
So x squared plus x minus 6 is another factor?
Is the other factor, correct? So what we have so far is we have the factor we already knew of, x plus 1, and then we get the quotient here, the result of division, as we saw was x squared plus x minus 6. So that's how we've factored our function so far. Does anyone have any questions? And again, from this quadratic, x squared, we're getting these other two factors here. So now we've got to figure out, how does the quadratic factor? Once you end up with a bunch of things times a quadratic, you don't need synthetic division anymore. You can either factor the quadratic by saying what are two numbers that multiply to give me -6 and add to get 1. If you don't know those two numbers, what else could we do?
Synthetic division.
You could do synthetic division, but it's not necessary. Yes, certainly you could. Or the quadratic formula. What does the quadratic formula on a quadratic like this give us? The zeros, right? The solutions, the zeros. Once we know the zeros, like if I came up with this, this isn't right, but if I came up with x equals 2 and x equals to 3 from the quadratic formula, those are the zeros. We would then know all the corresponding factors to those zeros, right? If x equals to 2 is a zero of the quadratic, then what's the factor? -2x, -2x minus 2 is the factor. If x is equal to 3, what's the factor? X minus 3. So there you go. Those would be your two factors of that quadratic. If you know the zeros, you know the factors.
Doesn't that give you 4 total factors?
No, that gives you 2, right? Because these two are the result of factoring this quadratic. Those two would go here and here. So I'm going to erase that because that's not accurate. With this quadratic, it's much easier. What are two numbers that multiply to give me -6, and the same two numbers add to get +1? Say that again.
3 and -2.
X plus 3, x minus 2. Do y'all agree? All right, so there we have the quadratic factored. 3 factors in total is how the x cubed plus x squared minus 5x minus 6 factors. So at some point, you have to go through synthetic division. It's super inefficient to say, all right, well, we just plugged -1 in and that worked. So I had that factor. Let me plug a +1 in. Let me plug a +2. Let me plug in a -2, a +3, a -3. And just keep going through that list until you find 3. It's highly inefficient and it doesn't always work. So if we have the 3 factors here, so this is our final answer. That's how that x cubed factors. We've got 3 factors there. Those factors correspond to the zeros of -1, -3, and +2. And what did we say was another way to describe our zeros on the graph? The x-intercepts, right? So not only do we have the factors, we have the zeros, which are the x-intercepts of that graph. So let's just verify that visually. And we'll just graph our function that's given to us. And so notice what we came up with was that function was the same thing as x plus 1 times x plus 3 times x minus 2. So you can see that, maybe not on that other board, but hopefully from here that they're exactly the same function. Nonetheless, here's an x-intercept at -3, corresponding to this factor. Here's an x-intercept at -1, corresponding to this factor, and our x-intercept at 2, corresponding to that factor. Does anyone have any questions? So I'll just put this here next to our final result. So we can see. No one has any questions? That's kind of what all this culminates to, is being able to do that. All right, so then we're going to sort of have back up again. What we were asked is x plus 1 a factor? So they started off by giving us something to test. If we found that x plus 1 wasn't a factor, then we might move on to -1, +2, -2, and so on and so on and so on, right? An infinite list of numbers to I guess, attempt into the polynomial, because all we're looking for is a specific x value that gives us a 0. From there, we start dividing. But we need that one number that gives us a 0 as the remainder. And if we just started off blindly in any function, you're going to have essentially infinitely many numbers that could do that. So then the question is like, where do we start? This theorem, the rational zeros theorem, gives us a starting point. So when we're asked to factor something, this is what we're going to start with. And what it gives us is, it gives us a finite list of possible rational zeros. So remember, rational zeros, what they mean is just numbers in the form of p over q. So like rational numbers are all the whole numbers, positive and negative, but they're also any combination of division of those things, like 1/2, 2/3, 15/16. Those are rational numbers as well. So not only the whole numbers, but fractions as well. Does that make sense?
As long as
They can be negative as well, yeah. So they could be positive 1/2 or negative 1/2. That's, both of them are still rational numbers, because they're the quotient of two numbers, two whole numbers.
What's the definition of rational and irrational?
Rational is a number that can be expressed like this. Any rational number can be expressed at p over q, where p and q are whole numbers. So any whole number 2 is a rational number, because we can write 2 over 1. -10 is a rational number because it's really -10 over 1, but also fractions as well. 1/2, -3/4.
So 1/3 would be irrational.
1/3 is rational because 1/3 is rational because we can write it like this. It's the quotient of two whole numbers.
But if you wrote it as a whole number, it would be 0.233333.
Right. So rational numbers have a definite pattern to their decimal expansion. If we say 0.333333 forever, even though it's infinite, there's a definite pattern. It's always 3. A number like 0.12121212 forever, that's also a rational number.
So pi is irrational.
Pi is irrational because there's no pattern to its decimals. There's no repetition, and there's no specific pattern to them. They're just random numbers.
So a rational number does not include a mixed number.
A rational number is a mixed number. Like if I wrote 1 and 2/3, that's really 3 times 1 plus 2. That's really 5/3. So those are all rational numbers as well. Yeah. Does that make sense? Are there any other questions about?
So there's not a whole lot of irrational numbers.
There are infinitely many rational numbers.
There's not a whole lot that I know. Then.
Yeah, just take two numbers. Take any two whole numbers, divide them. That's a rational number. 1,032,032 divided by 1,035,035. That's a rational number.
Irrational?
Rational.
Oh, I meant irrational.
Oh, irrational. Yeah, yeah. I don't know if there's infinitely many irrational numbers. I think there are.
Welcome to that.
Yeah. Like it's ridiculously deep. I reached a point where I was like, I'm out. I'm out. So the idea is this theorem, given a specific function, this theorem will give us a finite list of numbers that we can try to plug in to see if we get a 0. So what it's saying, if we, yeah. I guess I could scoot that up. But what that theorem says is, given a specific particular function, the possible rational zeros are all of the factors of your constant term divided by the factors of your leading coefficient. So remember, the constant is the one that doesn't have an x attached to it. The leading coefficient is the number attached to x with the highest power. So for instance, in this example, the 6 is the leading coefficient. That's our leading coefficient. The positive 2 is our constant. So in order to come up with a list of possible, now keep in mind that's the key operating word here. These are possible rational zeros. It doesn't mean they're all or any of them that we come up with are guaranteed to actually be zeros or factors.
So if we went through all of them and we didn't get any zeros, would there not be any zeros for the equation then?
There wouldn't be any rational zeros for the function, right? Could be irrational, could be that they're imaginary. We wouldn't be able to find them. So that's something worth pointing out. Like I could have a function that was just the result of x minus root 3 times x plus root 3, right? These two are irrational. The theorem would never find those zeros for us, this theorem that we're using, nor would synthetic division find those zeros for us. We would have to specifically know to plug in root 3 or negative root 3 into that function. And there's nothing in our tool shed that gives us any indication that we should look for those. At this point, anyways. So let's write this out. I'm just going to abbreviate it. Possible rational zeros are the factors of the constant. So what are the factors of 2? 2 and 1. But it can also be negative 2 times negative 1, right? So we're just going to include the positive and the negatives. Factors of 2 divided by the factors of 6. 1, 2, 3, and 6. But we actually have to divide these numbers. As it is, it's just factors divided by other factors. Again, we're just going to include positive and negative, but you have to divide 1 by all these numbers on the bottom. So we have this 1 divided by 1. We have 1 divided by 2, 1 divided by 3, and 1 divided by 6. And then we have to divide this 2 by all of those numbers. 2 divided by 1. 2 divided by 2 is 1. We already have that listed here. 2 divided by 3. And 2 divided by 6, which is 1/3. We already have that here. So these are the possible rational zeros of that 6x to the 4th function. And again, what this does, this list that we've just generated of these 2, 4, 6, 8, 10, 12 numbers, these 12 numbers are the only 12 numbers that we would ever try with synthetic division. Plug a 1 into the function, does it give me a 0? If yes, then I start synthetic division with that factor. If no, I'll move on to -1. If no, I'll move on to +1/2 and -1/2. If that doesn't work, I'll move on to positive and -1/3. And then hopefully somewhere along that line, at least one of those things will give us a 0. That way we don't have to guess +1, -1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So like in something like this, if we tried 1 and -1, 2 and -2 as whole numbers, then we're totally out of whole numbers to try. So you could go on forever trying +-3, +-4, +-5, +-6, forever and ever, and none of those would ever give you a 0 in this function.
So this is just giving you like somewhere to start.
Exactly,
And
yeah.
end, really, because it takes away the infinite possibilities and breaks it down.
Yeah, exactly. That's all this is doing. It gives us a finite list of numbers that could potentially work with synthetic division versus an infinite list of numbers.
So there's 2 options on the test then. Either it doesn't zero out, or we did it wrong.
Yeah, right. Right. I'm not going to give you something that doesn't factor
Okay.
over some real numbers or
So
some
we-
rational
We
numbers.
just
Yeah.
did it wrong.
Yeah. Okay. And so we can do that with any function we're given, like 7x to the 5th, et cetera, in order to find the starting list of possibilities. We're just going to take, again, possible rational zeros. We're taking the factors of the constant, which is 4. Factors of 4, 1, 2, and 4. And we're dividing all of those numbers by the factors of 7, 1 and 7. And again, don't leave your list like that unless it's absolutely clear to you what those numbers are. It's really all the numbers on top divided by all the numbers on bottom. 1 divided by 1, 1 divided by 7, 2 divided by 1, 2 divided by 7, and 4 divided by 1, and 4 divided by 7. So again, 12 numbers to try in synthetic division. Or with the remainder theorem. We've done both. So if we're factoring the 7x to the 5th function, how many factors should we have at the very end when we've totally factored it? 5, right?
I have a question.
Yeah.
Where'd you get 12 numbers to try?
Because we have +-1, +-1/7, +-2.
Never mind.
Yeah.
I was overthinking.
So it's always the positive and negative of factors of the constant over the factors of the leading coefficient. All right, any other questions on that? So when we're asked to factor something like g of x, this is what we want to start with. We want to generate a list of numbers that have the potential to give us a 0 remainder or a factor. They're one and the same. So the rational zero theorem only gives possible rational zeros. That list doesn't tell us whether 1 or 2 or 3 or 5 or 7 of those are in fact zeros. It's up to us to explicitly show or determine that those numbers that we come up with could be factors. It's saying it only applies to functions with integer coefficients or whole number coefficients. So like if we had p of x as x to the fourth minus 1/6 x cubed, etc., what we would need to do is clear the fractions first and write it like this, and then apply the rational zero theorem to q of x, because it only applies to whole number coefficients. Don't worry, you won't see anything like this anyways, but it's definitely worth mentioning. Okay. Any questions? And honestly, on the exam, I'll have you write out these factors that we found, but I'll also give you a particular zero, so you don't have to like spend time checking all of those numbers. So like I'll give you at least 1 0. A couple more theorems that can sort of help us, like if you have it known in the back of your mind what you're looking for, these theorems can help. But every function defined as a polynomial of degree 1 or more has at least one complex zero. And what we mean by degree, this term degree is just the highest or largest power on x. So like for example, if we had a function that were 2x to the fourth minus 3x cubed plus x minus 5. We just look, in order to determine what the degree is, we just look at the highest power on x, which is 4. So this polynomial here is a degree 4. So complex zeros, it could be a plus bi, right? Or it could be 5 or 10 or negative 36. So just remember from 1.3 that all of our real numbers are classified as complex numbers as well. We've been using this theorem, the number of zeros theorem, to say like if I start off with a x to the 5th power, once it's completely factored, I should have 5 factors. So that's the number of zeros theorem is where that comes from. So a function defined by a polynomial of degree n has n distinct zeros. If we have n distinct zeros, that means we have n distinct factors. Remember, if we know a zero, we know its corresponding factor.
Are we gonna go into an example that has like 5 or 6?
I probably not.
Are we gonna have to know how to do it?
Yeah, the process is the same. You break it down until you have like linears times a quadratic. That's always our end, sort of our ending step, because then we factor the quadratic or solve the quadratic. So like for example, if we have like x to the 4th minus 2x squared plus, I don't know, 4. And we'll write it here, but this polynomial has a degree of 4. That means we know we're done factoring this thing completely when we have 4 distinct factors. Now, some of those factors could be the same, right? Like if these two were the same, we would just write it as one thing squared. So it could take that form, but you gotta know like this really is 2 factors here because it's to the 2nd power. So that's something we can use like as a quick check. Like if you're factoring something and you only have 3 factors, you look at that and you say, well, I've not completed that. I need to find that 4th factor. And this conjugate zeros theorem here, it's basically saying like if you have a complex solution, then its conjugate will also be a solution. So complex numbers, for whatever reason, they show up in complex pairs. So like if we knew that, I don't know, x equals 1 plus 2i is a 0 or a factor, then implicitly what's implied by this theorem, or what's explicit in this theorem, tells us that if 1 plus 2i is a 0, the conjugate of that number, 1 minus 2i, is also a 0. But we would like explicitly see the complex solutions coming out when we solve our quadratic. Like in that previous example we factored, you know, we had like a x plus 1 times a quadratic. This thing just had solutions of, or zeros of like 3 and 2 or whatever they were. But if at any point you're looking at some quadratic in your work, you don't know how to factor this, you use the quadratic formula to solve, that's, at this point is when you would come up with those two like imaginary solutions when you're solving the quadratic. So I hope that makes sense. Again, we've seen a lot of this before, we just haven't put it all together. So complex conjugates show up or complex numbers as zeros show up in conjugate pairs. Which again, it's just another check. Like if you say 1 plus 2i is a 0 and then you're done with that, it's only half the story, right? 1 plus 2i is a 0, you automatically get 1 minus 2i is the other 0. Again, this is for complex numbers, wherever it says that.
Total is 6 plus 2i, and 6 minus 2i would be?
Yes, exactly. Yeah. If 6 plus 2i were a 0, then automatically you should have 6 minus 2i as a 0. Or vice versa, right? If 6 minus 2i was your 0, you should also have as 6 plus 2i as the other 0. But complex numbers with this having real coefficients on the function do always show up in pairs, conjugate pairs. So I'm not going to test you over those theorems, like those individual one-offs that we've seen. They're all really just tools to help you completely factor something. So just look at them like that. Any other questions? Okay. We'll take a break, but what we're going to do is factor completely the 3x to the 4th minus 4x cubed, etc. Okay. So we'll do that after break. All right, so all of the stuff we've looked at, it kind of seemed overwhelming, but a problem like this would be the thing you'd want to focus on for the exam. In addition, I would say, you know, factor f into linear factors, state the zeros. I would give you one of the zeros, but we should also be able to find all of the possible rational zeros. Okay, so we'll say factor into linear factors and state the zeros, and we're also going to be given let's say we're given that x plus 1 is a factor of f of x. All right, the first thing we want to do, or to be able to do, is to find all of the possible rational zeros. And then notice, since we're given x plus 1 as a factor, that's going to tell us that corresponding value of -1 on this list that we come up with, we're just going to start with that in synthetic division, because we already know that's a factor. And again, to find the other factor, you need to do division. Okay. Another thing to realize is how these things sort of play out with our steps is that we're first going to factor f of x as a linear, the x plus 1 that we were given, times a cube. You know, whatever's here, I don't know. We haven't actually worked this out. But after step 1, you're going to have a linear times a cube. Then you go through another round of synthetic division to break the cube down. You'll still have this linear from the first step, but then this time we break the cube down as another linear, whatever it is, times a quadratic. So each round of synthetic division, you come up with like a linear x plus 1, x minus 2, and sort of one less power than you originally started with. So if we started off with this cube, the cube gets broken down into a linear times a quadratic. The quadratic will get broken down into two linears. So it's always a step-by-step thing how we factor these things. So you're never going to get all of the factors at once.
So once we have the next two linears, we would do synthetic division of both of them
Yeah,
to get whatever the next one is.
correct.
And should they equal the same thing?
Not necessarily. Like something could factor as like this is a fourth degree. So we would have ultimately when we're done we have 4 factors, right? So there's nothing telling us that this couldn't factor as something like this. Like we could have repetition all the way through. And again, we're not worried about that. All we're going to focus on is the process of finding a factor, synthetic division, finding another factor, synthetic division, and all of that stuff will come out in the end. We're not even worried about whether things repeat or not at this point.
Eventually, would it just keep repeating?
Eventually, well, it could. It depends on the function. Like you could have 4 totally different factors here. But the process of like synthetic division, that's the process we're repeating. And the whole time we're looking for 0 remainders. Okay. So the possibilities include, are the factors of our constant, which is 2. Remember our constant's really -2, but we already take into account the positive and the negative. So we're really just looking for the positive and negative factors of 2 divided by the factors of what? 3. The leading coefficient here is 3. Factors of 3 are 1 and 3. And again, it's all of those on top divided by all of the ones on bottom. So our list of possible rational zeros are positive and negative 1 divided by 1, 1 divided by 3, 2 divided by 1, and 2 divided by 3. So on the exam, you should be able to come up with that list. That's something I will ask you to do. Yeah.
You're not gonna make the number big, right? So you have to find a ton of factors.
No, like some of the ones on the homework are pretty ridiculous because they'll have like the factors of 37 and the factors of 125. But on the exam, it'll be pretty straightforward. Like the numbers won't be huge.
Is it going to ask us in the exam to find the possible rational zero?
Yes. Yeah, I will definitely ask you to find these. Even though I'm giving you one factor or 1 0 that works, I still want you to be able to find all of the possibilities. Yeah.
This one is a little bit complicated. I did the synthetic division x plus 1, and the other remainder is 0.
No, did you use -1?
Yeah.
-4, 1, 6. Okay, well let's check it out and see.
Okay.
Okay, so these are all of the possibilities for rational zeros to f of x, but we're given that x plus 1 is a factor. So automatically we know really 2 things, right? If I plug in x equals -1 into that function, I get a 0 as a remainder, but that doesn't tell me anything I already don't know. So the other thing is when this f of x, 3x to the fourth, etc., is divided by x plus 1, the remainder is 0. So we're going to take the x plus 1, and we're going to use synthetic division on that. Remember, that corresponds to an x value of -1. And our coefficients for the original are 3, -4, 1, 6, and -2. Okay, and then we're adding above the line. The first digit, 3, we're just going to drop that. And then we start multiplication. 3 times our -1 out here, -3, plus -4, -7, times now our -1, +7, plus 1 is 8, times -1, -8 plus 6, -2, times the -1 again, +2, which gives us this 0 here. So that's our remainder. And again, we were given that the x plus 1 here is a factor, which means that we should have a 0 remainder. The whole purpose of synthetic division is to get this other thing here. We're after all of that as a function of x. Okay. So, I'm going to just keep track of what we're doing up here at the top, just so we don't have multiple instances where we're writing out what f of x is. And I'll try to fit it all here. But this 3, -7, 8, and -2 corresponds to what kind of function, or what function with regards to x?
3x cubed minus 7x squared plus 8x minus 2.
3x cubed minus 7x squared plus 8x minus 2. Do you all agree with that?
Plus
Okay.
8x.
Huh? 8x, yeah, thanks. 8x minus 2. So how do we know after this first round of synthetic division, how does that tell us f of x and its factors? Or what does that tell us about f of x and its factors? That f of x factors as what? Yeah. X plus 1, remember it's the divisor. Always when you have a 0 remainder, you have two factors. The divisor is a factor, and the quotient is the other factor. So we have the original function now as factoring as x plus 1 times our quotient, 3x cubed minus 7x squared plus 8x minus 2. Are there any questions? So we're done looking at 3x to the fourth minus 4x cubed plus x squared. We're totally done with that. What we're focusing on now, it's almost like it's a completely different problem. Now our task is to factor 3x cubed minus 7x squared plus 8x minus 2. So I would highly recommend that you keep separate synthetic divisions going, because a lot of times what I see is people just want to build off of this right here and then put their next synthetic division here and try to divide that and then have all these numbers under here, and it just becomes really messy, and there's a huge tendency to report the wrong numbers when you do that. So every round of synthetic division should just look like what we have here. I mean, that's going to be my recommendation to you.
Should we use the same PRZ or?
Yeah. Yeah, and the nice thing about the potential rational zeros that we've come up with is they don't change. If they're possible rational zeros to the original 3x to the fourth, then anything that we use, or anything that we get as we break it down, it's still applying to that as well. So we could say, all right, well, I'm starting with now 3x cubed minus 7x squared plus 8x minus 2. Let me find the possible rational zeros of that, start over again. But there's no need to. Like, this list that we come up with will always be valid.
Well, since you already know 1 is a possible factor, would you just skip that and move on to the
No, so like, because we know -1 is a 0, when we're now factoring this 3x cubed, we wouldn't overlook that again, because it could be a factor as well. There's nothing that tells us if it's repeated.
So we'd start with -1.
So you might try to start with -1 again, but here's the list. We start with 1 and -1, 1/3, -1/3, 2, -2, 2/3, and -2/3. So just because a factor gives you a 0 remainder doesn't mean you cross that off the list ever.
So you just keep breaking it down until you just have a regular factor.
Yeah, exactly. Yep. Yeah. So like, right. It's like if we say we're asked to factor 320 and we say it's 160 times 2, right? We wouldn't just stop there and say I'm done factoring. Now we've got to take 160 and factor it, and then the factors of 160 perhaps also need to be factored. So it's kind of the same situation. Right now we're looking at a number like 2 times 160. We got to break down that 160 again, which for us is the 3x cubed minus 7x squared. Okay, any other questions before we go on? Okay, so we're gonna sort of, this work right here, we're gonna just ignore it because that's pertaining to the original function, and we've already broken the original function down. The process that we're using is exactly the same though. And we'll just note that here. Now factor 3x cubed minus 7x squared plus 8x minus 2. And our possible rational zeros were 1, 1/3, 2, and 2/3. So unfortunately, we were only given one factor. They didn't give us two factors where we could just immediately now take this step and do synthetic division. Now it's up to us to find factors from this list or zeros from this list in this function here. Is everybody clear on that? Okay, so then we're just going to start, and maybe we start in order. So maybe we're going to start in order, and again, we can go through synthetic division with each one of these, because at this point, we're just looking for a 0 remainder. When we have a 0 remainder, the thing that gave us the 0 is the thing we're going to use in synthetic division. So at this point, we could synthetic division on 1 and -1, 1/3 and -1/3, et cetera, or we could just use the remainder theorem to see which one of those is going to give us a 0, and then start division with that thing. So let's try, I don't know, x equals to 1, and we're plugging that into, I don't want to call this f of x because my original function was called f of x, but I'm going to plug this into the thing that we're trying to factor, the 3x cubed minus 7x squared plus 8x minus 2.
Is it okay to do it with synthetic division if you want to?
Yeah, totally. We can totally go through synthetic division here too if we want. All we're using is the remainder theorem here, but yeah, you can definitely do synthetic division with 1. I don't know if I actually computed that, but yeah.
It's 1/3.
So this is whatever. We're just gonna label this as not being 0. Did you already find it? Yeah. So, you know, naturally we're probably just gonna go through this list in order. Okay, 1 didn't work. We're gonna try -1 into that function. this point, like we said, we're just looking for something in here that gives us 0 in return. This is not 0 either. I didn't actually compute the value, I just know it's not 0. Okay, so far no success. Our next number off the list, we've tried positive and negative 1. Our next number is positive 1/3. So let's see if x equals 1/3, what do we get? So 1/3 into the function. So even though we have all these like tools, you notice like at this point, we're still fairly limited on how we have to approach it. At this point, it's just trial and error. There's really no way around it if you're doing these things by hand. Okay, so x equals 1/3. We have 3 times, what's 1/3 cubed? Or what's 1/3 times 1/3 times 1/3? 1/27th. The 3 over 27, or 3 times 1/27th there, minus 7 times 1/3 squared is 1/3 squared. 1 times 1 on top, 3 times 3 on bottom. So 1/9, or 7 over 9, plus 8 over 3. Or 8 times 1/3 minus 2. Okay, so sadly, since our lowest denominator is 27, our smallest fraction, I guess, is the 27th, we need all of these as a 27th. So that one's fine. 3 27ths minus 7/9 is how many 27ths? Yeah, right. We gotta multiply 9 by 3 to get a 27 down there. That means we gotta do that to the 7 as well. You know, most of you hopefully are plugging that into your calculator because it's tedious, right? Like on the exam, you have time constraints. Hopefully you're familiar with your calculator enough to just evaluate this. But we're gonna show that it is 0. Okay, so 7/9 minus 21 27ths plus 8/3. How many 27ths is 8/3? Get up.
72.
72. 72 27ths. And how many 27ths is our 2? 54 27ths. And now that we have the same denominator, we just subtract and add across the top and put it all over 27. So we have 72 minus 54 minus 21 is minus 3, plus the 3 on top gives us 0 over 27, and 0 over 27 is equal to 0. We can't divide by 0 on the bottom, but 0 divided by some number is always 0. Okay, so again, more than likely, you're just using your calculator to evaluate that. We see that when x is 1/3, we get a 0. And again, this is the remainder theorem. I've plugged in 1/3, I've got a 0, my remainder is 0 when that thing is divided by x minus 1/3. So now we're ready for synthetic division because we have a number that gives us 0. We have a factor. So we're going to use synthetic division at this point with the number that gave us our 0, which was 1/3. And remember what we're dividing is that polynomial here, the 3x cubed minus 7x, etc. So we have our 3x cubed minus our 7x squared plus 8x minus 2. So again, this process, I highly recommend that you have this completely separated from the process above, because you're going to get different numbers. All right, so now we start the process of synthetic division here. Addition above the line. Drop the 3. Multiply 3 and a third. 3 times a third is 1. Plus 7, or sorry, plus negative 7 is negative 6. Times negative 6 times a third gives us negative 2. Plus 8. Positive 6 times a third again. 6 times a third is a positive 2. Plus negative 2 is 0. So again, what we're dealing with here is the factor of the x equals to a third. That corresponds to what factor? X minus 1/3 multiplied by our quotient. This stuff right here is our quotient. Those numbers correspond to what in terms of x? Yes, that is 3x squared minus 6 times x plus 6. So remember, this isn't the original thing factored, right? That's not the original 3x to the 4th function factored. This is how part of that factors, because this is our 3x cubed minus our 7x squared plus 8x minus 2.
And now we'll plug that into the quadratic formula.
Yeah, now we're going to use the quadratic formula. But before we do that, let's go back up to the very beginning, because what we have now is a factored version of the 3x cubed. Is everybody okay with where we're at? Again, you always end up breaking these things down, these polynomials down one at a time. Okay, so we'll write what we have. Our original factor from the first step is still present, x plus 1. We then found that x minus a third times the quadratic, 3x squared minus 6x plus 6 is how that, everybody see that? This right here was just the factorization of this piece right here. Okay. Any questions on where we're at or what we've done? So it's a lot to stitch together, but you see that the process is the same every time. Find a 0, divide it in synthetic division, and you just sort of chip away at it. So now it's essentially we've got to start over. We have to factor our quadratic, 3x squared minus 6x plus 6. But again, we're now just dealing with the quadratic. You can synthetic division on that with our possible rational zeros like we did in the previous 2 steps, and that might be good practice. But with quadratics, all we need to do is just factor it or use the quadratic formula on it. Okay. So what I would do with this Before I use the quadratic formula, personally, I would take out the greatest common factor first, just so your numbers aren't as large. So we're just going to factor out that 3. And now we're going to focus on factoring the quadratic x squared minus 2x plus 2. So are there two numbers that multiply to give us positive 2, and the same two numbers have to add to get negative 2? The only factors of this 2 are 2 and 1. Is there any combination of 2 and 1 that when we add them gives us a negative 2? No. If this were minus, it would be a minus 1. If this were a minus, it would, you know. So like, that doesn't work. If this were negative, doesn't work. If both of them were negative, doesn't work. So there aren't any factors where we could just immediately factor that quadratic as two things. So we can't factor it that way, but again, we could solve the quadratic for when it's equal to 0 and then turn those zeros into factors. So that's what we're going to do. So then we'll just make a note here. Use the quadratic formula. And our quadratic formula tells us that x is equal to the opposite of b, which is negative 2. So we have the opposite of negative 2 plus or minus the square root of b squared, negative 2 squared, minus 4 times a times c. And then we have to divide all of this by 2 times a.
And you could do it with the first one too, right?
Yes,
A
right.
and 3 and
Of course, yeah. You could also use the quadratic formula on this as well, with a being 3, b being negative 6, and c being 6. Okay, so we've just got to figure out what these two numbers are here. We've got 2 plus or minus the square root of, what do we have on the inside of, or underneath the radical? What is it? Negative 4, right? Because on the inside here, this is a positive 4. Minus 4 times negative 2 times 1 is negative 8. So under the radical, we've got 4 minus 8, which is minus 4. All over 2. So that tells us right there, the square root of negative 4 gives us our imaginary solutions, right? Or numbers, complex. Which is why we couldn't simply find two numbers that multiplied to give us 2 and added to get negative 2. Okay, so we're going to simplify. What's the square root of negative 4? 2i. So 2 plus or minus 2i on the top, and it's all over 2. How does that simplify?
Plus or minus I.
Yes, everything divided by the 2 on bottom. 2 divided by 2, plus or minus 2i divided by 2. In other words, our two solutions are 1 plus I and 1 minus I. So those are both the values of x that make our quadratic 0.
So the 3 that you factored out earlier, it's done. It's been factored out,
Right.
Right.
Yeah, it's still kind of hanging out, right? It's still hanging out up front, but we're ignoring it. Or again, you could have used the quadratic formula with the 3 and the negative 6 and the positive 6. Your answers would have been 3 plus 3i and 3 minus 3i, at which point you would just factor a 3 out. So it's kind of the same in the end. But with these zeros, remember, we're trying to factor the original function. We have zeros here. What are the corresponding factors? So we get two factors from our two zeros, but what are they? If x equals to 2 is a 0, what's its factor? Right. If we said x equals to 2 is a 0, then its corresponding factor is x minus 2. Do you all agree with that? So if I say 1 plus I is a 0, what's the corresponding factor? Yeah. To get the corresponding factor, you just do x minus the 0. That's always the pattern. X minus that 0. And then the second factor is, again, x minus the other 0. Oops. X minus the other 0, 1 minus I. So you can totally leave it like that. It's just, maybe you prefer to write it as x minus 1 minus I and x minus 1 plus I. Either way, it's the same thing. So of course we would have never been able to find all of those two factors. But this is what we're looking at for the factorization of our quadratic. After we pulled that 3 out, that's how x squared minus 2x plus 2 factors. So there's the quadratic completely factored. Now, the disadvantage of trying to, at this point, if you were to do synthetic division on the quadratic, you clearly see that you don't end up with any rational numbers as a solution. So you would have gone through the list of 1 and negative 1, 1/3 and negative 1/3, 2 and negative 2, 2/3 and negative 2/3, and none of those would have given you a 0. So you think you'd have like this much work that didn't yield any fruit. So I would always just recommend when you start off with when you have a quadratic to try to factor it or do the quadratic formula. That way you're not wasting time. So all of this stuff, all of that stuff that we just wrote out in the box here, that has to then go in place of this quadratic here. And we've ran out of space. So I'll just copy that. But we just need to rewrite the 3x squared minus 6x plus 6 as this factored version here. Is everybody okay with that? You've got to break the quadratic down. And I don't know, I would recommend writing it out step by step, because if you've just got a bunch of synthetic division and then you're trying to piece it all together, I think there's a tendency to get confused as well. Okay, so there was our original function. We had, after 2 rounds of synthetic division, broken it up into this function, or these factors, and now we know how to break up this quadratic. So we'll have our x plus 1 times our x minus 1/3. And then we had 3 times x minus 1 plus I times x minus 1 minus I. And that's the same as our original function. So there's f of x factored into its 4 linear factors. Does anyone have any questions? And when we have the factors, we also have the zeros. So our zeros are x equal to -1, positive 1/3, and then we saw 1 from the quadratic 1 plus or minus I. So those are our 4 zeros. So that's kind of difficult. It's tedious, but like we said, factoring is tedious. So try to at least start on some of this so you don't get too overwhelmed with all of it. Also, the worksheets on D2L, you could look at those keys to see other examples if you need to. We'll finish up 3.3 Wednesday though, so I'll see y'all then.